Every atom in your body passed through a wall to get here. That sounds like a metaphor. It is a description of quantum mechanics that physicists have confirmed in laboratories for over 100 years. And the strangest part is, what happens when you try to watch it happen? In 1801, a British polymath named Thomas Young set up one of the simplest experiments in the history of science. He aimed a beam of light at a barrier with two narrow slits cut into it. Behind the barrier, a screen. If light were made of particles, you'd expect two bright bands on the screen, one behind each slit, like spray paint through a stencil. Young saw something else entirely. The screen showed a pattern of alternating bright and dark stripes, an interference pattern. The kind of pattern you get when two waves overlap, their peaks and troughs amplifying or cancelling each other out. Light was behaving like a wave. Fine. Physicists adjusted their models and moved on. For about a century that seemed settled. Then quantum mechanics arrived and broke everything. By the early 20th century, physicists could fire individual particles, one at a time, through the double slit, single electrons, single photons, one by one like bullets from a gun. Each particle hit the screen and left a single dot. Particle behavior, exactly what you'd expect. But as thousands of individual particles accumulated on the screen, those single dots formed the same interference pattern Young had seen with his beam of light. Stripes, waves. A single electron, fired alone, was somehow interfering with itself. As if it passed through both slits simultaneously, as if it explored every possible path and then landed based on probability. The math describing this, the wave function, treated the electron as a spread-out cloud of possibility until the moment it struck the screen. Then the cloud collapsed into a single point. That was strange enough. What came next dissolved the floor. Physicists wanted to know which slit the electron actually went through. A reasonable question. So they placed a detector at the slits, a device that could register which path each electron took. The moment they turned that detector on, the interference pattern vanished. The electrons started behaving like particles. Two bands. No stripes. No waves. The act of measuring which path the particle took changed the outcome of the experiment. Turn the detector off. Waves return. Turn it on. Particles. Every single time. Sit with that for a second. The electron seems to know whether it's being watched. When left alone, it behaves like a wave of possibilities, passing through both slits, interfering with itself. When observed, it picks one path, one reality. The measurement itself forces the outcome. This became known as the measurement problem, and it has haunted physics for a century. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, offered the most direct reading. The particle exists in a superposition of states until a measurement collapses it into one definite state. Before observation, the electron has no single position. It occupies a probability cloud. Observation is what pins reality down. Now, some physicists push that idea further. Eugene Wigner, a Nobel laureate, argued that consciousness itself was the trigger for collapse. His thought experiment, known as Wigner's friend, imagined a scenario where a conscious observer inside a sealed lab measures a particle, but the person outside hasn't looked at the result yet. Is the system still in superposition from the outside perspective? Or did the friend's awareness resolve it? Wigner believed consciousness played a direct role in determining physical outcomes. John von Neumann, one of the greatest mathematicians of the 20th century, built a formal framework that left room for exactly this. His mathematical treatment of quantum mechanics placed the cut between the quantum world and the classical world at the point where a conscious mind enters the chain. The equations, at least, permitted it. So where does reality live before someone looks? The double-slit experiment keeps pointing toward the same uncomfortable answer. Nowhere definite. Here is where a skeptic would push back, and they'd have good reason to. Many physicists argue that measurement has nothing to do with consciousness. A detector at the slit interacts with the electron physically, exchanging photons or energy to determine its position. That physical interaction, the exchange of information between systems, is what collapses the wave function. Consciousness is irrelevant. A camera with nobody watching the footage would produce the same result. The electron doesn't care whether a human brain is involved, it cares whether something interacted with it. This is the decoherence model, and it handles the math elegantly. When a quantum system becomes entangled with its environment, when it exchanges information with surrounding particles, the superposition bleeds away into the noise of the larger system. The wave function doesn't collapse. It spreads out into so many entangled particles that the interference pattern becomes undetectable. The appearance of collapse is a statistical inevitability, with or without an observer. That explanation satisfies most working physicists, but it sidesteps a question it can't quite close. Delayed choice experiments, first proposed by John Wheeler and carried out in labs starting in the 1980s, added a layer that decoherence alone struggles to absorb. In these setups, the decision about whether to measure which path the photon took is made after the photon has already passed through the slits. The choice happens too late to influence the photon's behavior. And yet the results still match. If you choose to measure the path, even after the fact, the interference pattern disappears. If you choose to let it go, the pattern returns. The photon's past behavior appears to change based on a future decision. Wheeler himself said it meant the past has no definite existence until it's recorded in the present. He wasn't being poetic. He meant it as a description of this in 2000, using entangled photon pairs. One photon hit a screen while its entangled partner was routed through a system that either preserved or erased which path information. When the which path data was erased, the interference pattern reappeared in the correlated detection of the partner photons. The choice to erase happened after the first photon had already been detected. The timeline ran backwards, or at least our assumption that effects follow causes in a fixed order ran into a wall. This is where the interpretations start to buckle under their own weight. The many worlds interpretation says every possible outcome happens in a branching universe. The electron goes through both slits, and reality splits. You only experience one branch. Decoherence says the wave function never collapses, just becomes untrackable. The Copenhagen interpretation says the observation creates the outcome. Objective collapse theories propose that superpositions break down spontaneously at certain scales, regardless of observation. Each framework handles some experiments beautifully and sweats through others. What none of them can do is remove the observer from the equation entirely. Even decoherence requires a system boundary, a line between the thing measured and the thing doing the measuring. Where you draw that line changes the physics. And at the end of every causal chain of measurements, of detectors detecting detectors, detecting particles, someone opens the file. Someone looks. You've felt a version of this outside the lab. You've agonized over a decision, run scenarios in your head for days, and the moment you committed, every alternative evaporated. The life you almost chose stopped existing. The paths not taken became unreal in a way that felt physical, like doors slamming shut behind you. Quantum mechanics suggests the universe might work the same way, except the doors were never open to begin with. They were probability clouds that your interaction shaped into a hallway. The double-slit experiment has been replicated with electrons, photons, atoms, and even molecules containing over 800 atoms. The scale keeps increasing. The weirdness holds. Every time we assume that sufficiently large objects will start behaving classically, the interference pattern appears and reminds us that the boundary between quantum and classical is one we drew for our own comfort. Richard Feynman called the double-slit experiment the only mystery of quantum mechanics. He said all other paradoxes were just variations of this one. A particle that exists in multiple states until interaction forces a single outcome. A universe that keeps its options open until something, somewhere, regests as a result. Whether that something must be a conscious mind remains the open wound at the center of physics. The equations permit it, the experiments can't rule it out. And every attempt to close the question opens two more, like a slit in a barrier that keeps producing patterns nobody predicted. The next time you make a choice, any choice, consider the possibility that you're doing exactly what that detector does at the slit. Collapsing a cloud of maybes into the single thing that happens, the universe might have been waiting for you to